We learned that an inverse can be used to solve a system of linear equations that when in the form ax equals b, where we recall that a contains the coefficients of our variables, the vector x contains the variables, or sometimes we call this the solution vector, and b is a vector containing our constants. So the A matrix, if we were to think in terms of an augmented matrix, is what we would have in the leftmost portion of our matrix, and then we augment that by the vector b. And the coefficients here are of, we have two variables, x and y, of three variables, x, y, and z, or whatever we choose to call those variables, and then any constants that we have appear on that right-hand side. Now, to solve this, we learned that multiplying both sides by A inverse gives us the identity matrix on the left, and the identity matrix multiplied by any vector or other matrix leaves that matrix or vector unchanged. It's like multiplying by 1. And the vector x can be found by multiplying A inverse B. Now this is if it exists. So we'll get into that in a moment here. Let's talk about how the inverse of a 2 by 2 is actually calculated. So suppose that we have a 2 by 2. We'll focus just on the 2 by 2 here in this video, and we'll call the components across the first row A, B, and C, D across the second row. Now if it exists, the inverse can be found by the following sort of formula, if you will. 1 over the quantity A times D minus B times C. So we can think about this as a scalar multiplier. This is just going to be some number. And then the matrix A sort of gets manipulated in a way. Notice that the value of D and A gets switched across the diagonal here in the inverse. And then what happens to B and C is they just get negated. Okay, so they just have negative signs there. And to show that this in fact works, let's consider a system, x plus y equals 10 and 2x minus y equals 2. We can write that as a vector equation, just as a reminder, as x times the vector 1, 2 plus y times the vector 1, negative 1. We can write in our coefficients of 1 and negative 1 here, equals the vector 10, 2. And then we can sort of unpack or undo the matrix vector multiplication, lift up the components of x and y, produce this vector here. And now we have our coefficient matrix A. We have our variable vector or solution vector x, and then we have our constant vector b. So we know that to find the solution, which in this case would be x, is equal to A inverse times b. Now, as we've noticed, most calculators will have a button that allows you to find the inverse, but we're just going to show that you can calculate the inverse and then just do the multiplication. So A inverse, so let's calculate A inverse here first before we plug it in, and that's going to be 1 over AD minus BC times the matrix where these two components get switched, the D and the A, and then we negate the B and negate the C and leave them in place. So in our case, we can see that A is 1, B is 1, C is 2, and D is negative 1. So to produce this result, we have 1 over A times D, so 1 times negative 1, minus B times C, which is 1 times 2. Multiplied by the matrix where we switch the 1 and the negative 1. So the negative 1 takes that position, the 1 takes that position. We negate the values of B and C, so negative of 1 is negative 1, and negative of 2 is negative 2. And so we've now constructed that matrix itself. So now we have to evaluate this scalar, which will be -1 minus 2 is -3. So we'll have 1 over -3, or -1/3 times our matrix. -1, -1, -2, 1. So when we multiply all 4 components by -1/3, we get 1/3, 1/3, 2/3, and -1/3. So right away we can see that A inverse is again not just 1 over each of the values. Notice that 1 over 1 and 1 over 3 are not the same. Now we need to conduct the multiplication, which we could do using technology, but we'll just go ahead and hand compute this here, since it's a smaller example, and just so we can see that everything does indeed work out. So when we multiply, we have 10 times the vector 1/3, 2/3, plus 2 times the vector 1/3, -1/3. This will give us 10/3 plus 2/3 is 12/3, and then we have 20/3 minus 2/3 is 18/3, and 12 over 3 is 4, and 18 over 3 is 6. So that's our vector x. That's what we've just found. Our vector x is equal to 4, 6. Now 4 is the value of x, 6 is the value of y, and we've just solved the system. And we can just verify 4 plus 6 is indeed 10. 2 times 4 is 8, minus 6 is in fact 2. And so we have found our inverse matrix. Now as a last point here, we just said when A inverse exists. So how could it not exist? Well, we have to turn our attention to the formula. And in the formula, we have to ask ourselves, what could go wrong? And we see that we have division by AD minus BC. And that value of that expression is going to, of course, depend on what A, B, C, and D are. And in some cases, that denominator could be 0. And when that denominator is 0, it's going to be impossible to find an inverse matrix. So that gives us enough to say, hey, as long as that denominator is not 0, we're going to be able to find an A inverse. So from the formula, we can see that a problem will occur when the denominator AD minus BC is equal to 0. This is called the determinant of A. In a way, you can think about it as it helps us determine whether the inverse exists. And we're just going to write this little theorem, which we've already sort of proven in language. A inverse exists for a 2 by 2 matrix as long as what we're calling the determinant of A, notice that we just use the abbreviation DET parentheses A, which is that denominator AD minus BC. As long as that is not equal to 0, A inverse exists. Now you might ask yourself, why are we computing inverses when we know we can solve a system with Gaussian elimination? Just because an inverse doesn't exist doesn't mean that the system doesn't have solutions. It just doesn't have exactly one solution. So there's the possibility where there are no solutions, or the possibility where there are infinitely many of them, and yet the inverse won't exist in those cases. So if Gaussian elimination allows us to determine all of those situations and whether there are 0, 1, or infinitely many, why would we compute the inverse? Well, they're going to be valuable later on when we're actually solving matrix equations. That is, equations involving matrices. We've seen one here where we can write something in the form AX equals B. Sometimes we have multiple matrices in an equation, and it's helpful to know if some of those inverses exist. Also, in our the future lesson, we'll take a look at the Leontief input-output model, and the inverse actually has a meaning, and a useful meaning. So there's kind of that twofold of it'll help us algebraically, and in some contexts it also has real-world meaning.